simple harmonic motion and uniform circular motion. When a particle executes simple harmonic motion, as you see, the particle is moving up and down along a rod. It is actually projection of the particle moving in a uniform circular motion. Let's see, this particle is actually moving with constant angular velocity omega in a circle. Let the radius of the circle be a, and as you see, as the particle goes round this circle, the projection of the particle, as you see, the particle is moving in the circle. Now let's check the projection of the particle on the screen on the right side. So the particle's projection or the shadow will execute simple harmonic motion. So we can say that simple harmonic motion is the shadow or the projection of uniform circular motion. Again, let's see the side view of the circular motion. And now if you see the side view, you will check the particle is moving as if it is in a rod, moving up and down about a fixed point, about the center of the circle. The center of circle here is the equilibrium or the origin. Let's see the shadow of the particle. As the particle is moving this circular path with a constant velocity, and its shadow is moving up and down. So uniform is the circular motion. Its projection is basically simple harmonic motion. Again, let's check the another animation. See, the particle is moving down in the third, fourth quadrant, and this is moving downwards. As the particle goes third to fourth quadrant, as you see it is moving up first to third, and now this is simple harmonic motion. So uniform circular motion is simple harmonic motion. Let's go for characteristic of simple harmonic motion. Let the particle be at P, making angle theta with the x-axis. Let's calculate the displacement, velocity, and acceleration. Okay, let's go for the part second. Okay. Characteristics of simple harmonic motion. See, let's calculate the displacement of the particle P, which is executing simple harmonic motion. So displacement is the position of the particle from the origin. So from P, draw two perpendiculars, PM and PN, on OY and OX. So we can calculate displacement here in right angular triangle of PN. You see that sine of theta is perpendicular or hypotenuse. This PN is actually OM and this is OP. So sine theta will be equal to OM. OM is actually Y. OP is actually A. So displacement is Y is equal to A sine of theta. But as you know, angular velocity is theta over t. Theta will be equal to omega t. So displacement of the particle at any instance of time will be a sine of omega t. This is the displacement of the particle. Amplitude. Maximum displacement of particle P executing simple harmonic motion from its main position. Basically, this circular motion is simple harmonic motion, as you see, and the amplitude is like maximum displacement of the particle P. So the maximum displacement will be when the particle reaches at Y and Y dash. When particle reaches Y, the shadow is at P, and when shadow is at M. When it reaches Y dash, shadow is at this, that is, it has maximum amplitude then. So displacement is Y is equal to A sine of theta, where theta is 2 pi by t, or it's omega t, as you have seen. So to calculate the displacement of this particle, you see this Y is maximum. This is A plus A, or this is minus A, only if sine theta is either plus 1 or sine theta is minus 1. When sine theta is plus 1, you see theta is pi over 2, and This is minus when theta is 3 pi by 2. Alright, or it is 90 degree or is 270 degree. Alright, see, when theta is pi by 2, y is plus a. The position of particle will be p. Now when theta is 270, this y will be minus a, because sine theta of 270 is minus 1. So the amplitude is either plus a or minus a when it's at p, or when it is at y or y dash. Now velocity, we can find the velocity of the particle executing simple harmonic motion by simply differentiating the displacement. So y is the differentiation of displacement. We can write it as y dash. So y is differentiation of displacement. What is displacement? A sine of omega t. So a is constant, then this will be a differentiation of sine theta is cos theta or cos omega t into differentiation of this angle omega t. Then the velocity will be a omega cos omega t. Alright. Now we can change this cos omega t in terms of sine of angle, sine of omega t, by using a simple identity. As we know that sine square omega t plus cos square omega t is 1. This cos omega t will be under root of 1 minus sine square omega t. Right? So sine omega t, which is actually sine of theta, that is perpendicular to the base, and you see that sine theta or sine omega t is actually y over a, y over. So we can write this as sine omega t, and we can write the value of sine omega t y by a in this equation. Then cos omega t will be, it will be under root of 1 minus sine square, it will be y square by a square, it will be a square minus y square divided by a square under root, this will be a. Alright, now what will be the velocity? Velocity will be a omega under root of a square minus y square over a. This will get cancelled, so we have velocity equal to omega times a square minus y square. Alright, now we have two different cases. Case first, at y is equal to 0, that is when the particle is on the x-axis, that is the shadow is at O, then v is equal to omega times a, which is maximum. So the velocity will be maximum at the origin when the particle is executing simple harmonic motion. Now at y is equal to plus minus a at extreme positions, then you see that a square minus and this a square will get cancelled. We will have velocity 0, that it will be minimum or it will be 0 at extremes, extreme positions. Okay.